Hello, everyone. Welcome to the new C++ Serbia meetup. This time we have Đorđe Nedić, and Đorđe will speak about atomics and lock-free algorithms. So probably this will be also one of the interesting presentations for me as well. This time we have some additional announcements. One of the official sponsors of C++ Serbia user group is JetBrains. And for all of you who are here, I'm sorry, folks, online folks, but this time this is for people who are physically here on the meetup. We have one giveaway license for all JetBrains products, and I think that license is valid for 1 year. This is something new. On every meetup in the future, we will have one giveaway for you. So this is the sponsorship of JetBrains, and thanks to JetBrains and their sponsorship. Without further ado, Đorđe, you have a word.
Okay. Welcome, everybody. My name is Đorđe Nedić, and thank you for the introduction. So today I will be speaking about atomic operations and lock-free data structures in C++. And to start off, why? So why do we need atomic operations? Why do we need lock-free data structures? For one, even if you've never written code that includes atomics, and even if you never read code that includes atomics, you might need to know about them, because your PC, your embedded device or whatever, its operating system, the libraries you use, frameworks you use, and everything else that powers today's world includes atomics somewhere. So I think when you are debugging and you see that, there's some funny instructions in the disassembly, this might be it, and it might help you. And why lock-free data structures? So I stole this image from Herb Sutter. I think it's great. Basically, lock-free data structures are something that's used very sparingly, and they have very specific use cases. So you might also never encounter them in the wild, but it's good to know that they exist. And the good thing about lock-free data structures is that they can avoid many of the issues we have with multiprocessing today. So priority inversion, deadlocks, they avoid that pretty good. And you also have some determinism benefits. So latency is much more bounded, and we can reason about the program much better than when using locks. So a bit of history. When I started working in embedded software, and this looks like something I worked on. And I wrote code for microcontrollers that run on unmanned aerial vehicles. And basically, you have a flight computer in most cases. You have many sensors connected to it. You have communications. You have logging. You have actuators that you need to move. And all of this needs to happen constantly. And it needs to happen at regular intervals for every device that you have. So what you do is use hardware interrupts. Basically, what a hardware interrupt is, when something happens on the hardware, not in the CPU itself. For example, you have some voltage on some pin, or you have some communication protocol receive data, then that will stop the CPU and execute the interrupt code. So that switches to a whole new context, and it looks something like threads on modern systems. However, there's only one stack, but that doesn't matter. So anyway, when you come into this problem, you ask your seniors, you Google, and everything you come up looks something like this. So it doesn't matter too much, but this is like the baseline of what you will get. And you either have some flag that you set after you receive some data in a global variable, and then you check that flag, and then you use the data, and you clear the flag. Or you have a queue, and you push to that queue. Again, you push to that queue in an interrupt, you pop it in the main thread of execution, and then you handle the data. So this code it's not portable. It's not pretty. but it works in a lot of cases, and that's why people keep recommending it. But towards the end of the talk, I hope that you will not be writing code like this. Now, most of you probably did not start in embedded software. I can't know that, but the situations you come across involve using C++ for one, using threads, modern CPU, where you will have lots of things and lots of problems that you don't have on microcontrollers. So let's move this example over. Let's move it to the traditional software development in C++. Still, you will be rarely seeing something like this, but it's a good analogy. And you have a flag, you have one thread, you have a second thread. One thread produces some data, sets a flag, the other gets it, clears it. So does anyone see a problem here? Now, there are two problems here. So the first problem is that while we are actually setting or clearing this flag, the CPU the scheduler might interrupt the thread that's doing it at the moment. And we are not guaranteed that this operation is going to be non-interruptible. So we might end up with bogus data that actually we cannot use anymore. So that might happen. But if that doesn't happen, another thing that can happen is the compiler and your CPU today will be able to reorder stuff. So it can reorder, do work and data ready equals false. It can reorder produce data and data ready is true. And that's something that's not as easy to solve. So previously, a lot of people used to rely on compiler intrinsics, inline assembly, their operating system mechanisms, stuff like that. But in C++11, finally, we got a way to do this in a standardized manner. So now we can include std atomic, and we can make this flag atomic. Okay, good. Now, both of these problems are actually solved this way in this specific case. However, there's something under the hood. So when we are actually reading or writing to this variable, we are implicitly using a certain memory ordering. And there are actually 6 types of memory ordering we can set on an atomic operation. And by default, we're using the sequential consistency one. But let's start off from the weakest one. So first up, we have memory order relax. And this guarantees that any load or store with this memory order is atomic. So it cannot be interrupted halfway. However, it gives us no guarantees on what will happen with other loads and stores in that thread, or at all. So next up, we have acquire and release, and these are a pair, so they work together. Acquire is used with the load, and release is used with the store on the same variable. So what happens when we use those two is basically that we get some guarantees. Other than the operations individually being atomic, now everything that happens before the store with the release memory ordering must be visible to the other thread that loads that variable with acquire. And the order is not guaranteed, but everything must be visible at that point. And next up, and also this prevents your compiler from reordering in the same thread across that boundary. It creates a boundary even for the current thread. So no loads or stores might go across that boundary. Now, we have memory order acquire release. This is the same thing essentially, but you don't have to think about whether something's a load or a store, and okay. And next up, we have sequential consistency. Now, this is the strongest one, and it's the one that's used by default. And basically, this gives us all the guarantee that acquire release pair with the load and store gives us. However, it also guarantees that the order of every operation before the acquire load actually before the release store must be visible in the same order in the thread that's reading with the acquire memory barrier. And lastly, we have memory order consume. Now, we don't need to talk about that one too much because It's still work in progress, actually. It's been advised not to use it. And it's supposed to actually do the same thing as acquire, but with weaker guarantees. So it's supposed to only give you guarantees for loads and stores that have a data dependency on the variable that's being stored with release operation. And we hope that, eventually this will get implemented in compilers properly, but right now it's acquire. So, and it's also advised not to use it. So we also don't know if some older compiler has a bug with it, so just don't use it. Now, if we actually take a look at what's happening with the previous example, this is what it's going to boil down to. So instead of just checking it, here's an explicit load with the memory order acquire and explicit stores memory order release. And you can see that the loads in thread 1 and the stores in thread 2 are paired. So we have 2 pairs. And what this means is essentially that we are creating a critical section in between those, and nothing can move out. And now we're going to take a look at the example. We're going to try to make a simple queue into a single producer, single consumer, lock-free queue. And please don't take this code as production code. This is just an example and doesn't consider many things. But it's good enough for us to understand the point. So here's a simple declaration of a queue. We have basically a templated class, and it has the data array. Inside of it, it's templated in terms of size as well. So we're not allocating, we're not doing anything fancy here. We don't consider basically nothing. And here's a push operation. So this is pretty canonical. Most of you have probably seen this. Here's a pop operation. And basically, what we're just doing is checking if it's empty, if it's full, then setting an element or reading the element, and then incrementing the write or read index, or head or tail, however you want to call it. So now we want to make this single producer, single consumer lock-free. And the first thing we do, we make the read and the write index atomic. So why do we need to do this? Precisely to get the guarantees that we were talking about. And let's take a look at that. So what the problem here is that this store to our local buffer, it can be, if we don't actually have these guarantees, it can be moved around. And basically what can happen is that at the same moment, 2 threads will have a data race, and you will try reading from an element which is being written at the moment, or vice versa, and that's a problem. Another thing is that basically reading the write and read index also needs to be atomic itself. What happens if you try reading something while it's being written and it gets interrupted? So yeah, we need both guarantees, both atomicity on the read and write index, and we also need the guarantees for visibility. So this is what it looks like. Basically, we are pairing the load of the read index here with the store of the read index here. And we are also pairing the load of the write index here with the store of the write index here. Please consider that the topmost load is relaxed only because the producer or the consumer is reading their own index. So they don't need to care about these things. It can just read its own. And so this is what it looks like, actually. Sorry. Let's move this. Okay, I also stole this picture. I didn't want to recreate it. It's too much effort. So take a look at this. It's basically the same thing. Even though the code is different, we can see the point is the same. We have 2 pairs of acquire release. And when we are incrementing the push cursor, it's paired with reading the push cursor here. And when we are writing to the pop cursor, we are actually, with the release barrier, we're actually pairing that with inquire. And when these two are combined, you see that these two are basically creating a critical section, locking each of the operations on the buffer inside. So each of the operations on buffers, on the buffer itself, must be visible before any next one. But this was a single producer, single consumer buffer, and we had two indices, and one was being only modified by one thread and another by another. So what do we do when we need to actually modify the variable from different threads at the same time? And we need a new tool here. So what's going to happen here? Does anyone know what the result here is going to be? Yes, it could be anything from 0 to 10. So we don't know. And it could also, even crazier things might happen, because I think it's also undefined behavior. So let's go on. And let's try to break this down. So what is the problem here? The problem here is that this increment of the var variable, it cannot be made atomic just by making the variable atomic. Why? Because we need to first load it, then we need to increment it, then we need to store it. Basically, this is how anything will be. This is how this code will be compiled. And if you take a look at how that looks, if you think as the CPU, this is going to happen. So the problem here is that a thread might get interrupted after it loads and before it stores. So what can happen is that another thread might think, oh, this is still 3, but it fell behind. More threads in the meantime have incremented the variable, and now it's actually 6. So it's going to take 3, it's going to increment it, it's going to store it. So now we're not going to get 7, we're going to get 4. That's not going to work. So the new tool that we get for this is compare exchange. And compare exchange, basically, what it does, it gives us a way to actually do a change of the variable in an atomic way. And the CPUs have instructions for this most of the time. Now, some embedded architectures might not have it. I know that Cortex-M0, for instance, doesn't have it, but yeah, that's another topic. But most CPUs today will have this feature. And this is a standardized way to do it. So if we take a look here, we have the expected, desired, and memory ordering for each, whether it's success or it fails. Now, why do we have all this? Because we are actually taking a value that's expected and then passing also the value that's going to be set if the expected value is still there at the time we're looking. And basically, if it's not, then it's going to read back into this temporary variable. And then we can do lots of things based on that. So one thing we can do is we can create a spin lock. So here we have a lock that's basically spins until it acquires, until it spins until it's acquired. And this is used everywhere. So your operating system uses this, libraries use this, it's everywhere. And that's, sorry, yeah. One thing we also need to go back to is why weak and why strong. So because this is sometimes very expensive on modern CPUs, the CPU might need to do a lot of stuff. It might need to invalidate some cache parts. It might need to, do other things. I'm not really sure, but the cache is the most critical one. So because of that, we have been given a way for the CPU to tell us, oh, this is too much effort. I'm not going to go through with this, and just say no. So with weak, we are actually giving the CPU a chance to say no. This is going to be too expensive. And with strong, we are not giving it that chance. We are saying, oh, you must do this, no matter the performance cost. So whether you're doing something that's, depending on what you're doing, you might need one or the other. And which one you use is really, it can be a big debate because it can really vary on the situation. Here we are using weak, but it doesn't have to be that way. So when we're spinning, I don't think that it matters that much. And now, okay, we have all of these tools in our toolbox now. There's one more thing we haven't mentioned, is that there's a special case for compare and exchange for Booleans. It's test and set, but yeah, it's the same thing. And now we're going to take a look at API design for lock-free data structures. I wrote a collection of lock-free data structures for things I was interested in, things I needed, and basically through that journey, I noticed that there are many, many ways to do it. And depending on what you need, you might go one way or the other. So let's go there. Now, the first thing you're going to see is whether it's a single producer, single consumer scenario, or if it's a multi-producer, multi-consumer scenario. And there are also variations. So you can have multi-producer, single consumer, and the other way around. And the biggest difference here is the speed. Like single producer, single consumer is the fastest way to do it. And code's complexity, storage overhead. So all of those things, they're much lower on single producer, single consumer. However, we also lose the flexibility. So we saw the queue. It's the queue I've implemented is very similar to that. We're not going to waste too much time. However, there are other things we can do. So in respect to, for example, whether we are working with single variables, single elements or multiple elements, we can create an API that's completely different. And we can basically lower the overhead of the atomic operations if we are actually working with multiple elements at the time. However, we lose some things. And the first assumption here I've made for this whole library is that all types will be trivial. So they will be trivially copyable and trivially default constructible. And this is a pretty big limitation for C++. So we can talk about that later. There are ways to do it in a different way. However, this is what I went with. And now what this gives me is a superpower. Basically, I can send and receive multiple elements at a time. I can also peek, and I can use memcopy for all of that. So a nice thing about this API is, if you take a look here, we also have this peek and skip. So just give me a second. So we can write multiple elements at a time, right? We can just pass a pointer, pass an array, pass a span, but we can also do something that's much more interesting. We can peek, and peek is essentially giving us back data without removing it from the buffer. Then we can use skip to actually remove the data manually from the buffer. And why this is useful is when you have some data that operations can fail on. So for example, we need to send it somewhere, but it doesn't get sent. Then we can use that. And one clever thing I did here basically is I use memcopy. So you will see here, because these are trivial types, you can just use two pass memcopy, one for the first linear part and one for the other, if it's wrapping, or just one. And in regards to that, there's also one more interesting thing you can do. So you cannot just, it's not just about removing, sending, and receiving data. You can also get access to the data. And I think the most interesting data structure here is the biparted buffer. And what it gives you is an ability to actually get access to contiguous data inside the buffer while you're actually working on it. So you can now get access to a contiguous space that's contains something or it's free for writing, while at the same time the buffer is used in another thread to write or read. And we actually have to do some clever things here. So we're going to skip over the API here, and we're gonna take a look at some diagrams. So this is a classic ring buffer. So you can write to it, you can read to it, you can read from it. When we have our read and write indexes, and we have marked a start of it here. And basically, this should work fine. So now we need to write. We need to acquire 4 slots for writing. And as you can see, here's our write index. We need 4 slots. We're going round and round and round, and we should get there. However, this is where the buffer ends. So this is what we have when we unroll the buffer. And so we cannot acquire 4 slots for writing. So what can we do? We can actually go from the start. So we have 4 slots here. Why should we have to take these ones? So we can take these ones. But now we have a problem. When we want to read the data, when we read this available data, now we have some free space that has no useful data. We don't know what it contains. And it's going to be next up for reading if we don't do something about it. So we can introduce a new index, an invalidate index, and we can use it to mark where the invalid data is at the end of the buffer. So now, when we get here, we're just going to skip over to the start for reading and read this part. But what happens if we want to write now? So we read this, we read the next area. Now everything here is free, and this is invalid, right? So now we need to write. But we have this much free data, this much free storage. So how do we write more than this? Well, it's simple. Because it's invalid data, we can just write over it and move the invalidate index. And the constraint is still here that both write and invalidate indexes in my implementation are actually only modified from the producer thread. So we can do this, no problem. So that's one interesting thing I don't see very often. You can play around with the API. And what you can do here is also you can modify data in place. So you can do zero copy stuff as long as the buffer is big enough to hold, while you're actually working on the data, to add more stuff in the background. You can do zero copy. You can do 5 passes of processing if you have the time for it, and then you can move it out when you need it. So one more thing that you can do on embedded systems is you can use the DMA. So DMA is a way to move data really fast without using the CPU. The CPU needs to tell the chip, we have this much data at this address. Wire all the wires up that you need to, and send this data while I'm working on something else. And you can do this. You can use this type of buffering to actually use DMA. However, there are some caveats, and that's that the DMA is not part of the CPU. So now you have to synchronize manually your entire chip. And yeah, it depends on the platform how you're going to do that. So that's just playing around with the single producer, single consumer API. However, there are also some things that you can choose. There are also some other API considerations. So for multi-producer, multi-consumer, this gets much more complex. And we're not going to go through the entire implementation here. For that, you can read Dmitry Vyukov's blog, or I can link it at the end, or you can read my implementation, which is based on his. And we're going to just take a quick look here. Oh, so, sorry. This is a pop operation, okay? And you can see that there's quite a lot of stuff happening here. And why do we need all of this? So the thing is, once you're no longer working with single producer, single consumer data structures, the assumption that only one thread can modify one index at a time does not hold anymore. But we already saw, we can use compare and exchange for that, but that's not enough because there's something that's called an ABA problem. And let's just give me a second. So the ABA issue is that this is an example from a log-free stack. But the ABA problem is that you can basically compare and exchange. However, if for some reason the variable has changed many times and is the same one that you expect to be, again, but the whole data structure around it has done a lot of things, it has changed. And this can happen if one core can get held up and threads can go on, and the buffer can wrap, and we can get to the same position. However, that's not the same element anymore, and there might not be an element anymore at all. It might be a free slot now. So in order to solve the ABA issue, there are many ways to do it actually, but what we did is basically each slot will have its own push count and pop count. However, we also have per queue monotonically rising counters. So now we can actually see if the counter changed. Now we know. If it's only our push count and pop count, if they're the same, then it's not okay until we are sure that the monotonically rising counter is the same as well. Unless you're really unlucky and you go through all 64 bits, which is not very, it's not going to happen. So that's one issue that we face with multi-producer, multi-consumer. And some other things that I have not talked about is, whether your data structure will use statically allocated memory or dynamically allocated memory. I don't think that matters too much. However, you can also store pointers to things. So, for the compiler, it's generally better to have statically allocated memory, but there are trade-offs there. However, there's also constructor destructor constraints. So if you want to work with non-trivial types, now you're getting into now you have to worry about many more things. And a great example of this is Eric Richtorp's SPSCQ. So what he does is interesting. So first off, he's using an allocator. He's getting some storage. It's not just a templated array. Next up, he gets a pointer to it, and what he does when he wants to actually push data to it is argument forwarding and using emplace semantics. So now, if you actually want to construct the object inside the queue, you have to forward all the arguments, and it has to be constructed inside the queue. And if your object is allocating memory, if it's holding a hardware resource, if it's doing anything at all, you need to do this. What I did is only constrained to types that don't do that. But now we have other problems. So what happens if we want to pop? So if we want to pop, we can't. We can do it in a way that uses the copy constructor, but then we have another problem. The next time we are using that slot and emplacing inside of it, we are actually calling the destructor of the object that's already there. So if that destructor is non-trivial, then that's a problem, right? So what he does is basically he only gives you the pointer to the front element, and you are to do with it what you want. And after that, you have to be a good boy, and you have to return. You have to actually move the index using pop. So you can see that there are very big API limitations when you start doing this. However, I think this is much more useful to CPP folks than for regular I don't know, embedded or HPC or some other very specific workload that doesn't need to hold resources, doesn't need to hold. I mean, you can do that, but yeah, this is more general. However, you also cannot do multiple elements at a time very easily. You have to loop yourself. You have to do all of those things, and also getting. You also cannot really. Yeah, sorry. So you have all those API limitations, but it can be done. It can be done. So moving over, there are some other things we have to consider. Sorry. Okay, so today we have very complex CPUs, and I already mentioned that sometimes atomic operations can have big overhead, and we need ways to actually avoid this, and we need to understand what's happening inside the CPU to avoid it. And one of the things that is happening that's very dangerous to performance is cache coherence. And well, actually that's something that's happening anyway, but the phenomenon is called false sharing. And it's when multiple variables that actually have no data dependency, no relationship to each other, they share the same cache line. So a modern CPU is not reading bytes anymore. When it reads memory, it reads groups of bytes. It calls a cache line. And this is much easier for its cache. So it reads, for example, 64 bytes on a modern CPU. And then if it decides, oh, I've read this multiple times, then it's going to cache it inside its own cache. And there are caches that are tied to a CPU core, and then there's the big cache that's not. So if the CPU loads a certain cache line into its cache, then now if anything changes there, and the second CPU core needs to access the same memory and modify it, for instance. And if the second CPU modifies that memory, now we need to invalidate that cache line inside the first CPU. Otherwise, we have wrong information. So if a variable was 1, and it's been changed to 1 million, why should we still look at it when it was 1? So we need to avoid sharing cache lines between things that are not dependent on each other. And you can see in my implementation, and if in Rigtorp's, for instance, this align as. So what's being done here is basically you align your index to cache line size, and that makes sure that it's going to start at that an offset that's a multiple of that. And if you do for all of these, then that's fine. Except in some cases where it's going to be fine. But now when the first CPU is modifying its own variable, if the consumer is modifying the read, or it's loading the read, and it doesn't actually need to change, it only needs to load it. For example, if the consumer is reading data but the producer is doing nothing, so why should we actually keep those two in the same cache line? And if the producer actually needs to modify the write index, but that's going to affect the read index as well. So we don't want to share this. And this is how we solve it. And also, there are some optimizations that we can do. So the implementations that I've showed you all use, for one, use an arbitrary sized buffer. Now, what we need to do there is we need to either catch wrapping, so see if we have reached the end of the buffer and zero the variable ourselves, or we have to use the modulus operator. And in the Q example, we were using the modulus operator. But we can also do another thing. If we constrain ourselves to power of 2 size, then we can use a binary mask. And essentially, that's the cheapest way to do wrapping adds or subtractions on any hardware. It's going to be faster because there's no branch prediction. For embedded hardware, modules is sometimes very, very expensive. It can be 10 to 20 cycles on some CPUs. Another thing we can do, and what Rigtorp did, was you can actually do a clever thing and cache the indexes. So if you're a producer and you've written 50 times you've written 50 times to the queue. However, the consumer did nothing at all in that time. So why would we need to actually load atomically the right index when we know we can actually, sorry, why would we need to atomically load the read index if we know that we actually have space? So this might be a little too much, I'm sorry, but let's go back to the picture. So if we are actually so this is free data. No, this is free space. This is data. And if basically we have not changed anything, we have not written anything, we know that the value is going to be the same as the previous one. So we don't need to atomically load it anymore, because the only reason why we couldn't, for example, read or write is if it's a queue empty or it's full. So for anything intermediate, we can write. So we only need to know if it's full or if it's empty. And if we keep the previous value, then we can just keep using that until we get to a scenario where it's actually full or empty, and then do the expensive atomic load. So even the relaxed load is going to be more expensive than just using the cache variable. Okay, and that's basically some optimizations that we can do. Now, so this is the demonstration of padding to avoid cache line sharing, to avoid false sharing. And this is something that can happen, okay? Basically, if we have a multi-producer, multi-consumer data structure, and many threads are trying constantly to write or read from it, then the time spent trying to actually acquire a slot is basically time wasted. For that time, a thread that has actually acquired the data or that has actually written the data can go on and do useful things. So another optimization, and something that's very often used, is backoff. And it's something that you're not going to see in this example. So it's something that we can only do in software, unfortunately. If a thread sees that 5 times I was unsuccessful in writing, maybe I should wait a bit. And there's exponential backoff, for instance, where every time you try, you know how much time has passed since the previous one. You can double it up to a certain point. And this is used in radio communication. It's used everywhere. So this is something that you can do. And yeah, basically, it can increase throughput. However, it does funny things to latency, which is something you should keep in mind, and which is the reason why this happens here. Finally, don't use volatile, okay? So volatile is not a synchronization primitive. And volatile has its purposes. However, it's very often being abused as a synchronization primitive. It does work on some architecture and situation combinations. It does work on some compilers, but it's not consistent. So first off, on anything more modern, it's not going to work. Why? Because it's not only the compiler that can reorder writes or reads, it's also the CPU. So today's CPUs have basically reordering capabilities for reads and writes. They are super scalar. They can do multiple reads and writes at the same time. And volatile only guarantees that volatile reads and writes in respect to each other are not going to be reordered by the compiler and not optimized out as well, but that doesn't matter right now. So, and also there's the constraint that they are only synchronized within each other. So in the examples I've shown, atomic reads and writes can also be synchronized with non-atomic reads and writes. And that's what we're using them most of the time. So don't do this. And that's it. If you have any questions, if I forgot something, we can go back and take a look.
Questions?
Okay, just for context, how many of you have written code which has atomics? And you have no questions?
Thanks. If you go a couple of slides back to the Slavia Square, so I'm thinking as maybe somebody who is running the city, do you think this problem can be solved by adding more lanes?
I think it's Amdahl's law or something like that that's going to apply. It's going to be a logarithm probably, but I'm not a traffic controller.
Yeah, so, I mean, then like changing to the structure of circular queue, do you think that adding more elements would maybe solve some of the...
More elements at the same time, or?
Just increase the capacity of the
increase the no, it's not going to solve problems. You can increase the capacity, but the threads are actually fighting. Well, if you have a queue that's full, you have not designed the queue well. So you should have a queue in production that's almost always empty if you're doing things right. And sometimes it can be almost full, but almost always it's empty. So if you have a bigger queue, it's not going to happen because the threads are fighting over. Read and write, counters, monotonic counters, and they are fighting for. Yeah, okay, it's going to be faster if they don't fight for the pop and push count for the specific element, but. Yeah, they're still going to be fighting over the monotonic revising counters.
Maybe on the topic of CPU and how it works, how it caches, maybe you could expand on the topic of cache coherence in CPU on different algorithms which are used.
Actually, I'm not an expert in cache design for CPUs, but the latest I think in that's used is MOAI. I forgot.
Messy. Right.
It was messy, but it was modified with something else. I forgot with what, and basically now that's the state of the art. But we don't actually know the implementation details for the latest chips because it's a trade secret. So Messy is the one that you should Google if you want to know how it works. And basically what we want is to avoid the I part. We want to avoid invalidation when it's not necessary.
I also have one question. So did you do any benchmarking when you wrote this?
Yeah, I did initially, but then I stopped. The reason is, for one, it takes quite a lot of effort, and two, I decided I don't care. The reason is that if you want super optimized implementations of all of these, you should not be using my library. There are some optimizations that I didn't use, like for example, power of 2.1, I did not do caching either. Why? Because I wanted it to be both embedded and regular, non-embedded software friendly, and then it would have to be configurable, and then the code would get really ugly, but I also want the code to be readable so people can actually learn from it. So I tried to get, middle ground that's gonna make the most people happy. But there are benchmarks that I would recommend looking at it. I think for multi-producer, multi-consumer, Dmitry Vyukov has a blog which goes into that. There's also FastQ for MPMC. That's also the author did a lot of benchmarking, and there's a good talk that was recently on CPBCon, which I stole the picture from, and this is the name of the guy. Okay, so you can Google this guy, and he actually benchmarked this simple queue with just one element pushes and pops and no other, API niceties. But he actually did this demonstration and implemented every optimization that he could find and that I could find. So you can actually look that up, and increases are quite big from his findings. When I tried replicating some of them, I could not. For instance, caching, I benchmarked that. I did not get a lot of benefit from it, but it was probably my setup that was wrong. So.
Also, do you know about the, and I'm not quite sure, it's probably not applicable to embedded, but the memory mapped pages thing for ring buffers.
Yes. Yeah, there's a trick. If you have an MMU, you can do a nice trick. You can map 2 pages to one basically memory region, and then you can give those to the producer and the consumer, and then you will basically have 3 atomics because each one has their own mapping. But yeah, I did not show that one. That's very obscure. I think that's done maybe in some operating system it's done, but I would have to Google that. So yeah, that's one trick you can do. But situations where you have access to the MMU manually and it's also not an embedded systems are very rare. Yeah.
On the subject of testing, on which architectures you tested your library?
So I tested it on x86, my desktop CPU, and I tested it on a microcontroller, Cortex M4.
So it is ARM, and I guess they have different guarantees when it comes to memory ordering.
Yeah, actually,
CPU
I forgot
offers.
to say that. Yeah. So different architectures have different memory ordering guarantees, and x86 has something that's called a strong memory ordering. What that means is that basically each load is an acquire and each store is a release in terms of ordering. However, the loads and stores itself are not atomic unless you do use atomics. But basically, this is almost free on x86 because you are mostly fighting the compiler. However, if you cross to ARM, then it's actually very expensive compared to x86 because it's very small on x86, and you need to specialize instructions. And I actually did have some links for Catbolt, and I forgot to show that. Sorry. Just a second. Oh, okay. So what we have here is the queue that we've already seen, and we are just pushing and popping from it and then asserting that it's fine. And if you take a look at the instructions here, there's nothing funny here, right? Compares, conditional moves, jump equal, moves, compares, loads. That's it, right? There's nothing really strange here. However, if we switch to ARM, now maybe not all of you are familiar with ARM syntax, but there's something funny here, and this is DMB instructions. So these are data memory barriers, and they basically prevent reordering in hardware. And the argument is just the level at which it's doing that. So basically, this is what gets generated because of that. And yeah, with many pipeline steps, with with superscalars as well, it's going to be more expensive than on a microcontroller. On a microcontroller, very, very cheap. It has 3 pipeline stages, no speculation, no out of order, anything, it's not subscalar. So yeah, however, this is probably going to get more complex in time. And there's also one other thing in ARM, it's DSB, that's used for the entire chip usually. So if you're using the DMA and you want to synchronize with the entire chip, that's DSB. So yeah, great question.
From the testing, have you ever experienced like bug in your code that was affected by the memory reordering, and how hard was it to find it if you had such problems?
Yeah, that's why I said like most people won't be writing, but I see that a lot of people actually are writing atomic code. So it's very hard to find issues usually. However, there are tools today that can help you. Previously, we did not have those. There are thread sanitizers, which will actually try to inspect your code at runtime and see if anything funny is going on. They will break the code. So that's good. But generally, these bugs are very hard to find. And if you don't have to write log-free code, don't. If you can use something that's well tested, do that. If you cannot use it at all, great. But there's certainly some benefits, and there are some situations where it's irreplaceable. So if you have some guarantees that you need to have, like immunity to priority inversion deadlocks, or strict latency guarantees, then you're going to be using them most of the time. So definitely very hard to debug. Okay.
Thank you.
Finally, I would like to thank CPP Serbia for helping us set this up, and all of you for coming.
Thank you, George, for the great presentation.